Hey, my friend, if you have trouble falling asleep and your mind won't switch off tonight, let's give it something gentle and precise to rest on. In this video, I'll walk you through how quantum theory actually works, calmly, step by step, so you can learn a little and fall asleep a lot. Chapter 1. The Quantum Rulebook: States, Predictions, and Experiments. Quantum physics is easiest to understand when you treat it as a rulebook for prediction. It is not, first of all, a collection of dramatic claims. It is a disciplined method for connecting what you do in an experiment to what you should expect to record. You prepare a system in a controlled way, you let it evolve under conditions you can describe, and you measure it with an apparatus that produces outcomes you can count. Quantum theory tells you which outcomes are possible and how often each outcome should appear when the same protocol is repeated many times. In that sense, quantum mechanics is less like a riddle and more like a contract. If you set things up this way and ask this question, you should see this pattern in the data. To appreciate why this is powerful, it helps to be precise about what an experiment is. An experiment is a repeatable protocol, not a one-time spectacle. You define a preparation procedure, you define a measurement procedure, and you repeat them many times. The detector output might look like a flash of light, a click in an electronic counter, a spot on a screen, a voltage pulse, or a line in a spectrum. Whatever form it takes, the key is that it becomes a stable record that can be compared across runs. The point is not that a single outcome is dramatic. The point is that the collection of outcomes forms a distribution. And distributions can be predicted, tested, and refined. This explains why quantum mechanics is often described as statistical. In everyday life, we ask for the outcome of a single event, but scientific laws earn their authority through patterns. Classical physics can often provide sharp, single-run predictions when the relevant variables are known, and it can explain why small uncertainties in those variables lead to small uncertainties in the result. Quantum theory is different. Even when you have prepared the system as well as your apparatus allows, and even when you have accounted for known imperfections, the rulebook usually does not specify which single outcome must occur. Instead, it specifies probabilities for outcomes, and it specifies them in a way that is not optional or adjustable by taste. The probabilities are part of the theory's core, and the test is whether repeated trials agree with them. The first pillar of the rulebook is the quantum state. A state is the object in the theory that contains everything needed to predict measurement statistics for that system, given a choice of measurement and the relevant conditions. This definition is deliberately operational. In practice, you do not discover a state by peeking inside a system. You define it through preparation. The state is tied to what you did, how you filtered the system, how you cooled it, how you polarized it, how you isolated it, how you synchronized it with a clock, and how you ensured the preparation is repeatable. When experimentalists say they prepared the same state, they mean that the same preparation protocol, checked against stable diagnostics, produces the same distribution of outcomes for the measurements they use to verify it. It is essential that a state is more than a list of probabilities for one particular measurement. If that were all it was, you would need a new description every time you changed your apparatus. Instead, the same state description can be used to predict the outcome statistics for many different measurements. That is why the state functions like a language. It is a compact encoding of what has been prepared, and the rulebook provides a consistent grammar that turns that encoding into predictions for different experimental questions. The same prepared state can yield one distribution when you measure one observable and a very different distribution when you measure another. The state is what ties those different questions together into one coherent predictive framework. The second pillar is measurement. A measurement is not a mystical act of attention. It is a physical interaction between the system and a measuring device, designed so that certain features of the system become correlated with macroscopic records. Those records are what you read and store: a detector click, a pointer position, a digital bit in memory. In the theory, a measurement is represented by a set of possible outcomes together with a rule for assigning probabilities to those outcomes from the state. What makes a measurement quantum is not that it is vague or magical. What makes it quantum is that the rulebook imposes strict relationships between the state, the measurement, and the probabilities. And those relationships have been confirmed in situations where classical probability rules fail. Now comes the distinctive balance at the heart of quantum mechanics. Between preparation and measurement, the state typically evolves in a deterministic way when the system is sufficiently isolated and the interactions are known. In other words, the rulebook gives you a precise transformation of the state as time passes. But the measurement outcome in a single run is not fixed by that evolving state in the way a classical trajectory would fix a future position. Instead, the evolving state determines a probability distribution over outcomes. Deterministic evolution of the state and probabilistic outcomes of measurements are not a contradiction in the framework. They are the framework. The theory is strict about both parts, and experiments keep confirming that this is the right kind of strictness. At this point, it becomes useful to separate two sources of unpredictability. One is fundamental in the rulebook. Even with a perfectly specified state, outcomes can be genuinely probabilistic. The other is practical: imperfect control, stray fields, thermal agitation, detector inefficiency, and unintended interactions with the environment. In real laboratories, these practical effects are always present, and a large part of experimental skill is devoted to identifying them, suppressing them, and modeling what remains. The reason this matters is that the rulebook's probabilities are precise statements, and you cannot test precision statements with a sloppy apparatus. The art is to make the experiment quiet enough that the distribution you observe reflects the state you intended, not the drift you failed to notice. Interference experiments illustrate why the state must contain more structure than ordinary probability bookkeeping. Imagine preparing a system so that there are multiple alternatives that can lead to the same detector outcome. Classical reasoning tends to treat those alternatives as separate routes whose probabilities simply add. Quantum theory predicts something stricter and stranger. The alternatives can combine in a way that depends on relationships encoded in the state, producing enhancement in some outcomes and suppression in others. What looks like a gentle pattern on a screen is actually a sharp diagnostic of the rulebook's internal logic. It is telling you that the state is not just a bag of chances, but a structured object whose relationships can affect future probabilities in a way that cannot be mimicked by ordinary ignorance about which route occurred. Spectroscopy provides another, quieter demonstration of the same predictive logic. When atoms and molecules absorb or emit light, The frequencies form sharp patterns. Those patterns reflect the allowed energy differences of the system and the rules governing transitions under electromagnetic interaction. Quantum theory predicts these patterns with remarkable precision. The key point is not that the theory gives a vivid movie of tiny objects orbiting like planets. The key point is that the state and measurement framework, together with the rule for time evolution, generates definite predictions for observable frequencies and intensities, and those predictions match what detectors actually record. This is one reason quantum theory became trusted so quickly. It did not merely explain an odd corner case, it explained the stable structure of matter that people could measure every day. Underneath these examples sits a mathematical architecture that is spare but demanding. States live in an abstract space where combining, transforming, and comparing them has exact meaning, and measurements correspond to mathematical objects that map states to probabilities in a consistent way. Time evolution corresponds to transformations that preserve the internal consistency of probability assignments. You do not need to write down the formal expressions to grasp what this architecture accomplishes. It enforces one coherent style of reasoning across many different experiments. You cannot choose probabilities arbitrarily for each setup and still keep the whole structure consistent. The rulebook insists that your predictions for one measurement must be compatible with your predictions for another, as long as they refer to the same prepared state and the same physical dynamics. There is also a practical feedback loop that makes the rulebook feel grounded rather than abstract. In many situations, you do not simply assume you have prepared a particular state. You verify it. You measure the system in different ways. You compare observed frequencies to predicted ones, and you adjust the preparation until the model and data agree within known uncertainty. Because experiments are finite, observed frequencies wobble a little from run to run, even when the underlying probabilities are stable. So experimentalists quantify uncertainty in their estimates and work to ensure that the mismatch between prediction and data is not a mirage created by limited sampling or uncharacterized noise. When the match persists across different laboratories, different devices, and different implementations, confidence in the rulebook grows, not as a belief system, but as an accumulation of disciplined agreement with reality. Seen from this angle, quantum theory is both humble and powerful. It is humble because it does not promise a classical-style narrative for each individual event. It is powerful because it is rigidly consistent. Once a state is specified, it constrains the statistics of many different measurements, and once dynamics are specified, it constrains how those statistics can change in time. The framework prevents you from inventing probabilities on the fly. It demands that every prediction be connected back to a well-defined preparation and a well-defined measurement. And because it is built to be tested against distributions rather than single moments, it is unusually resistant to being saved by hand-waving. Either the predicted pattern appears in the data, or it does not. So revisiting quantum physics begins with something steady. Method. Prepare carefully. Define your measurements clearly. Use the rulebook to predict distributions, and let experiment judge the result. The universe does not need to feel intuitive in order to be dependable. And tonight you do not need to chase every question to the bottom. It is enough to notice that the patterns hold, the rules remain consistent, and you can let your mind rest while nature keeps its quiet order in the background. Chapter 2. The Language of Quantum, What a State Really Means. In quantum theory, the word state is simple and yet easy to misread. In ordinary life, a state sounds like a hidden condition, a thing possesses, like a label on a box, full or empty, hot or cold, here or there. In the quantum rulebook, a state is not a secret sticker inside the system. It is the complete predictive description that connects a preparation procedure to the statistics of outcomes for measurements you might later perform, provided you stay within the same definition of what counts as the system and what counts as everything else. When you say you have prepared a state, you are making a claim about what patterns will appear in the data, not a claim that you have uncovered a tiny internal biography. This is why it helps to treat the state as a piece of language rather than a picture. Its meaning is not defined by the image it triggers in your imagination, but by what it lets you calculate and what experiments confirm. Different laboratories, using different hardware, can agree they are preparing the same state if they can reproduce the same statistical predictions across a suitable range of measurement settings. In that sense, the state is a bridge between an abstract formalism and the physical world. It is where the theory touches the apparatus, not through poetry, but through repeatable numbers on a screen. To see what is distinctive here, it helps to reflect on what complete means. In classical mechanics, a complete state, at least in principle, fixes a unique future for every variable you might later read out, assuming you know the forces and you ignore practical limitations. Uncertainty usually enters because you do not know the initial conditions well enough. In quantum mechanics, even the most careful preparation does not generally grant that kind of certainty for every possible measurement you could choose. Instead, the state gives you the best possible predictive content the theory allows, and that predictive content is usually probabilistic. The point is not that the world becomes vague, but that the rulebook's idea of completeness is different. Because of this, the quantum state is not merely a list of ordinary probabilities for one chosen question. If it were, you would need an entirely new description each time you rotated a polarizer, changed a detector setting, or asked a different experimental question. Quantum theory offers something more unified. One state description generates coherent predictions for many different measurement arrangements, and it enforces consistency between those predictions. The state is like a single sentence in a language that can be read in many contexts. Change the question, and you get a new distribution, but it is still the same sentence doing the work. A good way to anchor this is to remember that measurements are physical interactions. A detector does not simply reveal a pre-existing number. It couples to the system and produces a durable macroscopic record, such as a click, a flash, a spot on a screen, or a digital bit. Different measurement devices couple in different ways, and the state is the common input that allows you to compute the statistics of those records without inventing a new description for each device. The state summarizes what the preparation has made available for any later readout you choose to implement. Inside the state concept, there is a distinction that experimentalists rely on constantly: the difference between a pure state and a mixed state. A pure state represents the ideal of maximal specification for a given system within quantum theory. It corresponds to a preparation, that has not intentionally averaged over alternatives and has not lost relevant information into uncontrolled degrees of freedom. In that ideal limit, the remaining randomness in outcomes is not blamed on ignorance about what you did in the lab. It is treated as the irreducible statistical character of measurement outcomes given that preparation. A mixed state, by contrast, represents partial information or genuine physical mixing. It is the appropriate description when you've averaged over different preparations, when your apparatus drifts, when thermal effects introduce variability, or when the system is correlated with something you are not tracking. Mixed states are essential for describing real systems, including matter in thermal equilibrium and subsystems of larger correlated systems. Mixedness is not an embarrassment that appears only when you lose control. It is a central part of the language because the world is full of correlations and because experiments are built inside environments, not outside them. The subtle part is that mixedness can arise in two distinct physical ways. Sometimes it is simple ignorance. You might prepare one of several possible pure states, but fail to record which one occurred, or you might know that a control parameter wandered within a range from run to run. In such cases, learning the missing information would let you refine your description. But mixedness can also arise even when you are not ignorant in that everyday sense. If a system becomes correlated with an environment, then the subsystem you keep becomes describable only by a mixed state, even if the combined system plus environment could be described by a pure state. The mixing is not just in your notebook. It is in the structure of correlations you are choosing not to track. This teaches a quiet lesson about boundaries. A quantum state is always the state of a system you have decided to define, and that decision is guided by what you can control and what you can measure. In one context, the system might be a single trapped atom. In another, it might be a carefully chosen mode of light inside a cavity. In yet another, it might be a large collection of electrons moving through a crystal. The boundary is not arbitrary, but it is contextual. And it matters because the state depends on what you count as inside the boundary and what you treat as outside. In practice, the boundary is drawn where your control ends and where the influence of the rest of the world must be summarized rather than followed in detail. The mathematical form of the state is built to preserve predictive consistency across all the questions you can ask. In the simplest idealized setting, a pure state can be represented as a vector-like object in an abstract space. That structure is not decorative. It lets you compute probabilities from precise relationships between the state you prepared and the measurement you perform, and it lets you capture interference, where different experimental alternatives combine to reshape the final distribution. Interference is one of the signs that the state is doing more than tracking ignorance. It is carrying relational structure that can change what outcomes are likely, even when no classical story about hidden routes can reproduce the same pattern. For realistic situations, the state is often represented by a density operator, which is designed to describe both pure states and mixed states within one unified language. This representation is operational. It is the object from which you compute outcome probabilities for any specified measurement, and it is the object that evolves under the dynamics you choose. When the system is well isolated, its evolution preserves purity. When the system is open to the world, interactions with untracked degrees of freedom tend to drive the description toward mixedness. This is not a mystical collapse into vagueness. It is the practical and testable consequence of entangling with an environment you do not monitor and cannot perfectly control. This is also why it is misleading to think of a state as a permanent property the system simply has. A state is something you ascribe given a preparation and a boundary. Change the preparation, and the state changes. Change what you include in the system, and the appropriate state changes. Even without changing anything intentionally, uncontrolled coupling to the environment can transform a pure description into a mixed one over time. The state is therefore not a static label. It is a living summary of what has been prepared and what is being ignored. How do we know the state language is not just convenient fiction? Because it can be reconstructed and checked. If you repeat the same preparation many times and measure the system in a sufficiently rich set of ways, you can infer the state that best accounts for the observed statistics. This procedure, known as quantum state tomography, is a disciplined inference rather than a metaphysical claim. You never directly see the state. You see detector outputs, and you infer the state using calibrated models of your measurement devices and careful statistical reasoning. When those reconstructions predict new measurement statistics that you then observe, the state language proves its worth in the most scientific way possible. It earns trust by surviving contact with new data. This dependence on calibration is not a weakness of quantum mechanics. It is a feature of all careful science. What quantum theory adds is an unusually clear separation between what belongs to the preparation and what belongs to the measurement. The state encodes what you prepared. The measurement encodes what question you asked and how you asked it. The rulebook combines them into probabilities. When people say quantum mechanics is measurement dependent, the most stable interpretation is simply that probabilities depend on both the state and the measurement. Because probabilities are statements about what your apparatus will record given the way you set up the physical interaction. At this point, it is tempting to say the quantum state is just information. There is truth in that, but it can be misunderstood. The state is a compressed summary of predictive content. It is the minimal object that contains everything you need to compute the statistics of outcomes for the measurements you consider relevant. In that sense, it functions like information, but it is not private or arbitrary. Two careful experimental groups can converge on the same state description because they are constrained by the same public facts. The data patterns produced by repeatable preparations and well-characterized measurements. The state is information, but it is information with teeth, because it makes quantitative commitments the world can accept or reject. This is also where the state concept touches a long-standing interpretational tension. Does the state describe something real out in the world? Or does it describe our knowledge of the world? Different interpretations answer differently, and quantum mechanics itself does not force a single narrative. What the theory does force is the discipline of commitments. If you claim a system is in a certain state, you must accept the entire set of statistical consequences that come with that claim. That is why the state language remains stable, even while philosophical stories differ. The theory's success does not rest on a single metaphor. It rests on the reliability of the predictive structure. So the most scientifically secure way to speak is modest and exact. A quantum state is not a photograph of reality. It is a rigorously tested language for organizing expectations about measurements, given a defined preparation and a defined boundary between system and environment. It is the single object that unifies many experimental questions into one coherent predictive framework. Without states, quantum theory would collapse into a scattered catalog of unrelated probability tables for separate devices, and there is a gentle existential note hidden in that grammar. The state reminds us that understanding does not always mean holding a vivid picture in the mind. Sometimes understanding means having a reliable way to anticipate what will happen when you ask the world a question, and accepting that the world can be orderly even when it refuses to fit neatly into intuition. In the end, that is a kind of calm. Reality is not required to match our preferred stories in order to remain dependable. If there is a lesson to carry into the night, it is that prediction can be honest without being absolute. You are a temporary pattern of attention inside a larger lawful world, and for a little while you can simply rest inside it. Chapter 3. Symmetry, the hidden organizer of nature. Symmetry can sound like decoration, as if nature simply prefers pleasing balance. In physics, symmetry is not an ornament. It is a statement about invariance, a claim that certain changes in how you describe an experiment do not change the experiment's underlying predictions. If you move the same apparatus to a different place, rotate it as a whole, or repeat the same protocol at a different time, the basic laws are expected to remain the same. Symmetry is the discipline of separating what is merely a choice of description from what is physically real. This matters in quantum theory because quantum mechanics is a language for prediction. A theory that depended on where you placed the origin of your coordinate system or which direction you decided to call up would not be a theory of nature. Symmetry provides the backbone of universality. It tells you which transformations of viewpoint are irrelevant to the physics, and it tells you what must be true if the laws are to remain compatible with those transformations. In that sense, symmetry is not something you notice at the end, like a pattern in wallpaper. It is something you build into the foundations, because without it, the theory would collapse into a collection of local rules with no shared meaning. The most familiar symmetries are those of space and time. Translation symmetry says the basic rules are the same here as they are over there. Rotation symmetry says the rules do not privilege one orientation in empty space over another. Time translation symmetry says repeating a controlled protocol tomorrow is governed by the same underlying dynamics as repeating it today. These statements are not only comforting, they constrain what the laws can be, and they constrain what can change in an isolated system. Symmetry does not merely describe nature's habits, it limits nature's options. The deep link between symmetry and conservation is one of the central organizing ideas of modern physics. When a system's laws are invariant under a continuous symmetry, there is a corresponding bookkeeping quantity that remains constant for an isolated system. If the laws do not change when you shift time, then there is a conserved quantity we call energy. If the laws do not change when you shift position, then there is a conserved quantity we call momentum. If the laws do not change when you rotate the system, then there is a conserved quantity related to rotation, often described as angular momentum. The important thing is not the vocabulary, but the logic. Invariance forces accountability. When the rules do not privilege one version of the world over another, some quantity must remain balanced as the system evolves. Quantum theory takes this structure and uses it to organize what is otherwise a bewildering space of possibilities. In the quantum framework, a symmetry is represented by a transformation that changes how you describe the system while leaving predicted measurement statistics unchanged. This is subtle in a useful way. A symmetry is not merely a geometric move of objects in space. It is also a controlled transformation of the mathematical description of the state and the quantities that represent measurements. When that transformation leaves all predicted outcome distributions the same, the theory is telling you that you have changed your language, not the physics. Once a symmetry is present, it becomes a source of stable labels for states and processes. These labels matter because they compress complexity. Instead of tracking every microscopic detail, you can classify states by how they behave under symmetry transformations, and you can predict which kinds of changes are possible without doing exhaustive calculations. Symmetry becomes a shortcut that is not a hack, but a consequence of the theory's own internal consistency. Spectroscopy is one of the cleanest demonstrations of symmetry's organizing power. Atoms and molecules do not emit or absorb light at arbitrary frequencies. They produce structured patterns of spectral lines, and those patterns repeat across different laboratories with remarkable reliability. Quantum theory explains this by describing allowed energy states and allowed transitions between them. Symmetry enters at two levels. First, conservation laws constrain transitions because whatever happens must keep the accounting consistent. Second, the allowed states themselves reflect the symmetry of the physical situation. The shape of an atomic state in the quantum sense is tied to rotational symmetry, and that structure constrains how the atom can exchange angular properties with light. This leads naturally to what physicists call selection rules, which are best understood as symmetry constraints in action. Some transitions are strongly allowed because they are compatible with the symmetry properties of the initial state, the final state, and the interaction that connects them. Other transitions are suppressed because they would violate a conservation law or clash with a symmetry constraint. In real experiments, forbidden often means extremely unlikely, not impossible, because small effects, environmental influences, and weaker interaction channels can open paths that are closed in an idealized picture. Still, the overall pattern remains. Symmetry does not merely decorate the results. It dictates the scaffolding on which the results hang. Symmetry also explains why distinct quantum states can share the same energy. This phenomenon, called degeneracy, often arises because a symmetry makes distinct configurations physically equivalent. In a perfectly symmetric situation, rotating the description can transform one state into another without changing any measurable energy. Energy cannot distinguish between them because the symmetry says there is no preferred orientation. The symmetry gathers those states into families with shared properties. If you introduce an external influence that creates a preferred direction or preferred location, the family can split and the shared energy can separate into distinct values. This is not just a curiosity, it is a practical signature of symmetry and symmetry breaking, and it is used constantly in laboratory physics to probe the structure of systems. Not all symmetries are continuous like smooth shifts and smooth rotations. Some are discrete, involving a flip rather than a gradual change. Mirror symmetry, often called parity, corresponds to swapping left and right in a description. Time reversal corresponds to reversing the direction of motion in the mathematical description. Charge conjugation corresponds to swapping particles with their corresponding antiparticles. Historically, it was tempting to assume these symmetries were universally respected because they feel like natural extensions of the idea that physics should not depend on arbitrary conventions. Quantum physics taught us that nature is more selective. Certain processes violate some of these discrete symmetries, and the violations are not random accidents. They are structured, rare in some contexts, common in others, and deeply informative about which interactions are at work. Importantly, this did not make symmetry irrelevant. It made symmetry more diagnostic. When a symmetry fails, the pattern of failure becomes a clue about the architecture beneath. In the modern framework of quantum field theory, symmetry is built so deeply into the structure that even violations are constrained. Under standard assumptions, there is a robust principle that the combined operation of charge conjugation, parity, and time reversal is a fundamental symmetry. The existence of such deep structural statements is part of why symmetry is not treated as a superficial preference. It is tied to the consistency of the framework itself. Symmetry here functions like a load-bearing beam. You can renovate parts of the building, but some beams are required for the building to stand. Beyond symmetries of space-time and discrete flips, there is another category that is less intuitive at first because it is not a symmetry of physical space, but a symmetry of description. These are gauge symmetries. They express the idea that our mathematical descriptions can contain redundancy, where multiple representations correspond to the same physical situation. At first, that can sound like an annoying technicality, but it has powerful consequences. Demanding that observable predictions remain unchanged under this built-in redundancy restricts what kinds of interactions can exist and how they must be structured. In other words, symmetry does not merely organize what we see. It helps determine what is possible in the first place. Symmetry also teaches an important lesson about complexity. Without symmetry principles, the space of possible laws is vast. You could invent countless interaction rules that fit a narrow set of data, and you would drown in options. Symmetry acts like a filter. It forbids many possible terms and relationships, leaving a smaller set of candidates that respect the invariances we observe. That is why symmetry is used not only to interpret experiments after the fact, but also to build theories before new data arrives. The goal is not to guess wildly. The goal is to demand consistency with invariance and let that demand do part of the work. Just as important is what happens when symmetry is present in the laws, but not in the actual state a system occupies. This is spontaneous symmetry breaking. The underlying rulebook can be symmetric, while the realized configuration is not. A crystal is a familiar example. The microscopic laws do not prefer a particular lattice orientation in empty space. Yet when matter freezes into a solid, it selects a repeating pattern and thereby reduces the symmetry of empty space. This idea becomes a map for understanding phases of matter and collective quantum behavior. Symmetry classifies what is possible, and symmetry breaking classifies what has actually happened. Revisiting quantum theory through symmetry makes the subject feel less like a collection of isolated oddities and more like an architecture. The world is not a pile of unrelated events. It is a system whose rules repeat reliably under changes of viewpoint, and that repetition compresses complexity into patterns we can learn. Symmetry is part of why matter has stable structure, why experiments performed in different places can agree, and why a compact set of principles can illuminate phenomena that look very different on the surface. There is also a quiet existential reflection hidden in that steadiness. Symmetry does not promise that life will feel orderly, but it shows that beneath experience there is an impartial order that does not depend on your attention to keep running. The universe keeps its invariances whether you notice them or not, and that constancy is part of why anything remains recognizable from moment to moment. When your thoughts feel scattered, it can be strangely comforting to remember that the deeper rules hold without effort, and you can let yourself rest inside that calm structure for a while. Chapter 4. Conservation Laws: Why Reality Stays Accountable. Conservation laws are the quiet rules that keep nature honest. They say that certain quantities cannot be created from nothing or erased without trace when a system is genuinely closed. If you follow a process carefully, the accounting must balance. In quantum physics, where single outcomes can be unpredictable and where the microscopic world does not always match intuition, conservation laws provide a steady kind of certainty. They do not promise that you can foresee every detector click, but they do promise that whatever happens, the totals reconcile when you include everything that participated in the interaction. To understand what conservation means, it helps to think operationally. A conserved quantity is one you can define in terms of measurements and then track through time. Energy, momentum, angular momentum, and electric charge are classic examples. Each can be inferred from observations, from motion and heat, from recoil and forces, from rotation and polarization, from currents and electromagnetic effects. Conservation does not mean the quantity is locked in one place. It means the total for a closed system remains constant, even as the quantity flows between parts, changes form, or becomes stored in fields in motion. Quantum theory does not weaken these ideas. It clarifies where conservation lives. When a system is sufficiently isolated, its quantum state evolves lawfully under the interactions present. Conservation laws constrain which kinds of evolution are possible and which transitions interactions can produce. Measurement then adds another layer, because a measurement is itself a physical interaction. The system does not merely reveal an answer. It couples to an apparatus that produces a macroscopic record, and conserved quantities can flow during that coupling. In other words, conservation is not just a statement about the system you care about. It is a statement about the combined physical process, including the apparatus, the environment, and any fields that carry energy and momentum away. A simple example is the emission of light by an atom. An excited atom can drop to a lower energy state and emit a photon. If you track only the atom, it seems as if energy vanished. The moment you include the photon, the bookkeeping becomes clear. The photon carries away the difference in energy between the atomic states. Momentum is conserved as well. The photon carries momentum, so the atom recoils in the opposite direction. That recoil can be measured in precision experiments, and it is not an extra detail added for style. It is the conservation law doing its job. The same principle applies to detection. A detector click is not a free revelation. It is a physical process. The system interacts with a device, triggers amplification, produces heat, and leaves a stable trace in electronics or memory. That trace requires energy and involves momentum exchange at some level, even if the transferred amounts are tiny compared to everyday scales. The very fact that you can store the outcome as a durable record is evidence that the event has been embedded into the material world through an energetic process. You do not need to imagine a mystical observer effect to explain why outcomes become records. You need only accept that records are physical and that physical things obey accounting rules. Energy conservation in quantum physics shows up most cleanly in the stability of certain states and in the sharpness of spectra. When an isolated system is prepared in a state with a definite energy, the statistical predictions for many measurements remain stable in time. The system is not frozen in an everyday sense, but its observable statistics do not drift. When energy changes, it changes through interaction, and the energy difference must appear somewhere else, often as emitted or absorbed radiation, or as energy exchanged with a surrounding material. This is also where quantum mechanics adds a nuance that is easy to misinterpret. In real atoms, excited states have finite lifetimes because they couple to the electromagnetic field and can decay. That means the emitted light is not a single perfectly sharp frequency of infinite duration. It has a natural spread. This spread does not violate energy conservation. It reflects that the emission happens over a finite time and that the atom plus field form a coupled system. When you describe only the atom, you are describing a subsystem, and subsystems can have energy that changes because energy is flowing elsewhere. The overall accounting remains exact when you include the field and the environment, even if the subsystem description looks less rigid. Momentum conservation is equally foundational, though it is often less obvious because laboratory systems are rarely perfectly isolated from supports and walls. Still, momentum accounting appears everywhere once you look for it. Light carries momentum, so absorbing light pushes matter, and emitting light produces recoil. In carefully controlled experiments with cold atoms and ions, recoil and momentum transfer are not side effects, they are signals. Even in everyday situations, momentum conservation explains why radiation pressure exists and why lasers can exert measurable forces. The quantum description refines this picture, but it does not replace it with something lawless. It simply tells you how momentum exchange is distributed across outcomes and how it appears in statistical patterns. In solids, momentum conservation takes a slightly different flavor because momentum can be shared with collective motion of the lattice. When an electron in a crystal changes its motion, the lattice can absorb or provide momentum in the form of vibrations. The accounting still holds, but the ledger includes more participants than you might first imagine. This is a recurring theme. Conservation is simplest when you track the full closed system, and it becomes subtle only when you focus on a part and forget that the rest can carry away what the part has lost. Angular momentum conservation adds another layer of structure because angular momentum in quantum physics often comes in discrete steps. Light can carry angular momentum through its polarization, and matter carries angular momentum through motion and intrinsic spin. When light interacts with atoms, the total angular momentum must balance. This constraint is one reason transitions follow recognizable patterns rather than occurring arbitrarily. It also explains why changing polarization can change which transitions are likely. The system is not choosing in a human sense. The interaction is simply restricted by the requirement that rotational accounting must work out. Electric charge conservation is among the most robust accounting principles we know. Charge does not appear or disappear in ordinary processes. It moves. In the modern field-based description, this idea becomes local as well as global. That means charge cannot vanish from one region unless it flows out into another, and currents are the way the ledger stays balanced from place to place. This local bookkeeping underlies why circuits work predictably, why charge buildup produces electric fields, and why electromagnetic measurements are so reproducible across laboratories. Quantum theory gives a deeper description of charge and its interactions, but it inherits and preserves the same accountability. In quantum field theory, conservation laws become even more structural. Interactions are written in a way that respects the conserved charges of the fields involved, and those conserved charges constrain which processes can occur. This does not mean every process that respects conservation must occur. Dynamics and probabilities still matter. But it means conservation can forbid entire classes of events outright. That is why conservation rules are among the first filters applied when physicists evaluate whether a proposed reaction or decay is even possible. Quantum theory also teaches that some quantities people casually treat as conserved are only approximately so. Particle number is a clear example. In many low-energy settings, it is an excellent approximation to talk as if the number of particles stays fixed, because creation and annihilation are so unlikely that they can be ignored. But in the relativistic quantum field description, particles can be created and annihilated, and what remains strictly conserved are deeper charges and the total energy, momentum, and angular momentum of a closed system. This is not a loophole in conservation. It is a refinement of what the theory considers fundamental when you look at nature at its most general level. Another nuance appears when you focus on a subsystem rather than the whole. A small part of a larger system does not necessarily conserve energy on its own because it can exchange energy with its surroundings. This is true for everyday heating and cooling, and it is also true for delicate quantum systems in laboratories. A well-prepared quantum device can lose energy into uncontrolled degrees of freedom as heat, or it can gain energy from noise. Conservation has not failed. It has simply been applied to a boundary that is too small. This perspective is one reason researchers work so hard on isolation and control. They are not trying to defeat conservation. They are trying to make the relevant flows small, predictable, and characterizable, so the experiment is dominated by the interaction they intended to study rather than by the countless weak interactions that are always present. This is one reason conservation laws are so useful in scientific discovery. They function as a checklist for what must be accounted for, even when you do not yet know the detailed mechanism. If an experiment suggests energy is disappearing from a subsystem, you look for an interaction channel that carries it away. If momentum does not balance, you look for recoil absorbed by an overlooked part of the apparatus, or for radiation carrying momentum out of the region you measured. Apparent violations are not treated as permission to abandon the rules. They are treated as evidence that something has been missed in the description of the closed system. The boundary, or the interaction. Conservation also explains why quantum randomness does not turn the world into chaos. The rulebook can assign probabilities to different outcomes, but those outcomes are not unconstrained. Each allowed outcome must satisfy the same accounting rules. In scattering experiments, conservation of energy and momentum restricts which final combinations are possible, and quantum dynamics assigns probabilities within those constraints. Randomness lives inside guardrails, and the guardrails are part of why the universe remains predictable at large scales, even when individual events can be uncertain. And there's an existential reflection that follows naturally from this steadiness. Conservation is a reminder that change is rarely disappearance into nothingness. It is transformation and transfer within a larger whole. Even when your own attention feels depleted, the world is still balancing every exchange with quiet precision. You can let the days settle, knowing that beneath your thoughts there is a dependable order that does not ask you to hold it together, only to breathe alongside it. Chapter 5. Quantum Fields. Why Particles Aren't Tiny Balls. It is natural to picture the world as made of little objects moving through space like grains of dust. That picture works well enough for everyday life, and even for much of classical physics, because many macroscopic objects behave as if they are localized and persistent. But when you press into the microscopic realm with precision experiments, the tiny ball image starts to fail in specific, testable ways. Quantum theory still allows you to speak about particles in many contexts, but it quietly changes what a particle is. In the modern view, particles are not the most fundamental entities. Fields are. A field is not a mysterious substance that fills space like fog. In physics, a field is simply something that assigns values to every point in space and time, and those values can change and interact according to rules. The electromagnetic field is the classic example. Even before quantum mechanics, it was clear that light behaves like a wave in a field, and that electric and magnetic influences propagate through space with their own dynamics. Quantum theory keeps the idea of fields, but revises what it means for a field to exist and what it means to detect something. Instead of thinking of a particle as a tiny object that always exists as a localized lump, the modern framework treats what we call a particle as a discrete excitation of an underlying field. This shift was not made for philosophical reasons. It was forced by evidence and by the demand for a consistent theory that respects both quantum principles and special relativity. If you try to build a theory that treats particles as primary objects that carry quantum behavior, you can do a lot with it in non-relativistic settings. You can describe electrons in atoms, photons in simple optical experiments, and a wide range of low-energy phenomena. But as you move to higher energies or demand that the theory work in any inertial frame without contradictions, difficulties appear. A framework built on quantum fields resolves these difficulties by making the symmetry between space and time and relativity compatible with quantum behavior, and by allowing creation and annihilation processes that are observed in high-energy experiments. The field viewpoint also clarifies a simple empirical fact. Particle number is not always fixed. In many experiments, especially those involving electromagnetic radiation, it is natural to speak as if the number of particles changes. Photons can be emitted and absorbed. In particle accelerators, collisions can produce new particles that did not exist in the incoming beams. A theory that insists particles are permanent little beads has to treat these events as somehow exceptional. A field theory treats them as ordinary. Fields can exchange energy, and energy can appear as excitations of different fields. The ledger of conserved quantities stays balanced, But how many particles are present becomes a context-dependent way of speaking rather than a universal primitive. In quantum field theory, each type of elementary particle corresponds to a field. There is an electron field, a quark field, and fields associated with the interactions we observe. When these fields are excited in certain ways, detectors register events that look particle-like. Localized hits, discrete counts, individual tracks in a detector. That is why the particle language remains useful. But it is useful in the same way that the word wave is useful for describing ocean swell, even though the ocean is made of molecules. The particle is a robust, emergent description of how a field's excitations behave under certain conditions and how detectors respond to them. This helps resolve a common confusion. People sometimes hear field and imagine something continuous and smooth, then hear quantum and imagine something granular and discrete, and assume the two ideas clash. Quantum field theory is precisely the union of those ideas. The underlying field is continuous in the sense that it exists throughout space, but the measurable excitations it supports come in discrete packets when you ask certain questions, such as how much energy is carried in a particular mode of the field. This is analogous to how a vibrating string can support waves, yet the allowed vibration patterns depend on boundary conditions and can lead to quantized energies when the system is treated quantum mechanically. The discreteness is not a sign that the field is made of tiny pellets. It is a sign that the field's allowed excitations, under the rules of quantum theory, come in discrete units for certain measurable quantities. The vacuum in this viewpoint is not nothing. It is the lowest energy state of the fields. That does not mean it is filled with usable energy waiting to be extracted like fuel. It means the fields still exist even when no particles are present. The vacuum is a state of the fields, and it can have measurable consequences. Certain subtle effects, such as shifts in atomic energy levels and forces between closely spaced surfaces, are best understood as consequences of the field structure of the vacuum and how it changes when boundaries or interactions are introduced. The key point is not to romanticize the vacuum as mystical. The key point is that empty space has a well-defined physical meaning in the theory, and that meaning can be probed experimentally. Thinking in fields also clarifies why particles are not tiny balls. A tiny ball has a well-defined position at all times, and its identity is tied to being that localized object. A quantum field excitation does not behave like that. Depending on how it is prepared and how it propagates, it can be spread out, it can interfere, and it can be described in ways that make where it is a question whose answer depends on how you measure. The field picture does not deny localization in the detector. It explains it. Detectors are built from matter, which is itself made of fields and interactions. When a field excitation interacts with a detector, the interaction can produce a localized deposit of energy and momentum that triggers an avalanche of amplification, leaving a macroscopic record at a particular place and time. The localization is an event in the detector, not proof that the excitation was a tiny ball traveling with a definite path like a microscopic billiard. The field viewpoint is also deeply connected to the idea that interactions are local in space-time. In relativity, influences cannot propagate faster than light. Quantum fields are constructed to respect this causal structure. The field at one region of space can interact with the field in the same region, and the consequences propagate through the field's dynamics. This is part of what makes quantum field theory the modern baseline for describing fundamental physics. It is a framework that combines quantum statistical prediction with relativistic causality in a way that has been tested with extraordinary precision, especially in the domain of electromagnetism. It is worth pausing on what extraordinary precision means here, because it is part of why the field picture is not merely an interpretation. Quantum electrodynamics, the quantum field theory of the electromagnetic interaction, predicts certain measurable quantities with an accuracy that is among the highest in all of science. Those predictions are not about vague philosophical questions. They are about numbers measured in laboratories, such as the fine details of how electrons and photons interact. The match between theory and experiment is so tight that it functions like a stress test for the entire framework. A conceptual story that cannot survive precision is not physics. The field framework survives. Another reason fields feel inevitable is that they naturally accommodate identical particles. In everyday thinking, you can label objects and track them as individuals. At the quantum level, identical particles of the same type are not distinguishable in the same way. The field framework makes this natural. Excitations of a field are not tagged with individual identity labels. They are defined by the field's modes and the state of excitation. This is not merely a semantic point. It explains the statistics that govern fermions and bosons and the stability and structure of matter. The particle as a little ball picture struggles here because it wants each particle to be an individual object with a trackable identity. Field excitations are not individuals in that sense, and experiments agree. At the same time, it is important not to oversell the idea that particles are not real. Particles are real as observed phenomena. When a detector records a discrete event, it is real. When a cloud chamber shows a track, it is real. When an accelerator experiment counts jets and decay products, those are real. What changes is the underlying ontology you use to explain why those observations have the form they do. The field picture says that the best fundamental description is not a swarm of tiny beads, but a set of fields whose excitations, under certain conditions and interactions, produce particle-like events in detectors. That is a subtle but powerful distinction because it tells you where to look for deeper unity, not in the geometry of little balls, but in the symmetries and interactions of fields. Fields also reshape how you think about forces. In classical physics, you might imagine forces as pushes and pulls between objects. In the quantum field picture, interactions arise from couplings between fields, and what you experience as a force can be described as the exchange of field excitations or as the effect of a field background on motion and energy. You do not need to picture tiny messengers flying back and forth as literal pellets. It is enough to understand that the interaction terms in the field theory determine how excitations influence each other and how energy and momentum are transferred. This is a more abstract picture, but it is also a more accurate one, and it scales naturally from low-energy laboratory systems to high-energy collisions. There is a practical reason to care about this shift in a video that revisits quantum theory. The field viewpoint is one of the places where the topic becomes calmer rather than stranger once you accept it. The tiny ball image creates paradoxes because it demands classical identity and classical trajectories from a world that does not behave that way. Fields remove some of that friction. They tell you that what exists fundamentally is something spread through space, governed by consistent rules, and that what you call a particle is one mode of that underlying reality presenting itself to your instruments. In the end, the field picture is not a claim that the world is vague. It is a claim that the world is structured differently from childhood intuition. Space is not an empty stage with objects darting around on it. Space is a place where fields exist, fluctuate, interact, and sometimes ring like a quiet instrument, producing discrete excitations that our detectors register as events. If you let that idea settle, it carries an existential softness with it. You are not separate from the physical world looking in. You are made of the same fields, arranged into a temporary pattern that can think and notice. The universe does not need solid little beads to be real. Its reality is deeper than that, and tonight you can let your mind drift, trusting that the same steady rules continue underneath your rest. Chapter 6. Interactions. How nature does forces. When people first meet physics, force sounds like a direct push or pull between objects. A hand pushes a door, gravity pulls an apple downward, a magnet tugs at a paperclip. That language is useful at human scale because it matches experience and because it compresses complicated processes into a single idea. But beneath that familiar surface, nature does not deliver forces as invisible hands. What we call a force is the outward face of an interaction, the visible consequence of deeper rules that govern how physical systems influence one another. The word interaction is deliberately broad. It includes gentle deflections, chemical bonding, the resistance of matter to compression, the absorption and emission of light, and the transformations that occur inside atomic nuclei. Quantum theory does not treat these as separate tricks. It treats them as variations on one theme. A system state changes because it is coupled to something else. That something else might be another localized excitation, an applied field configuration created in the laboratory, or an environment made of countless uncontrolled degrees of freedom. In the quantum view, the basic question is not what force acts on this object, but what couplings exist and what state changes do those couplings make possible. This is where the field viewpoint becomes practical. If you imagine the world as tiny balls, it is tempting to imagine forces as arrows acting on those balls from the outside. In the modern view, the fundamental description is written in terms of fields and their couplings. A force is what a coupling looks like when you ask macroscopic questions such as acceleration, pressure, rigidity, or attraction. At the microscopic level, the coupling is not an extra ingredient sprinkled on top of the world. It is built into the laws, specifying how different fields can affect one another, and how excitations of those fields can be created, destroyed, deflected, or transformed. Scattering makes this concrete because it is one of the cleanest ways to ask, what happens when two excitations meet? You prepare an incoming state with known properties, let it interact in a controlled region, and record what comes out. A single run can be unpredictable, yet the distribution over many runs is stable. That stability is the signature of an interaction. It tells you how strongly the participants couple, which outcomes are allowed, and how likely each allowed outcome is. In a classical picture, a force bends a trajectory continuously. In quantum theory, it is often more faithful to think in terms of state transformation. The interaction does not merely shove an object along a definite path. It changes the quantum state. and the changed state determines a probability distribution for what a detector will record. Sometimes the identities of the participants remain the same while their motion changes, as in elastic scattering. Sometimes the interaction converts energy into new excitations, changing what particles you can detect afterward. Sometimes it rearranges internal properties, like spin or other quantum labels, without any dramatic change in the visible path. In every case, the force you infer from the outcome is a macroscopic summary of a deeper coupling that specifies what transitions are possible. Electromagnetism is a calm anchor because it connects smoothly to everyday intuition while remaining fully quantum. Charges create and respond to the electromagnetic field, and light is an excitation of that same field. When an electron is deflected by a nearby charge, the field description says the electron is locally coupled to the electromagnetic field configuration produced by the other charge. No influence needs to leap instantaneously across space. The coupling is local, and the field carries influence through space and time in a way that respects causality. The familiar electric and magnetic forces are the classical large-scale limit of that local coupling. The quantum picture keeps the same core idea, but speaks in the language of probabilities and state changes, rather than in the language of definite trajectories. The strong interaction shows why the word force can hide crucial structure. Quarks carry a kind of charge that couples them to the gluon field, and the behavior of that coupling depends on the scale you probe. At very short distances, the interaction becomes weaker in a technical sense, so quarks behave almost as if they are free within that tiny domain. At larger distances, the interaction does not fade the way electromagnetism does. Instead, it effectively confines quarks inside composite particles such as protons and neutrons. The force we name strong is not simply a stronger version of electromagnetism. It is a different kind of coupling with a different kind of long-range behavior. Confinement has a striking consequence for intuition. Pulling quarks apart does not lead to a gentle weakening. Instead, the interaction stores energy in the field between them, and that energy can reorganize into new particles. The lesson is that what looks like a force can also be a rule that reshapes what the system can become. The weak interaction is different again. It is responsible for transformations that change one type of particle into another, and it plays a central role in nuclear decay and in the reactions that power stars. In everyday life, it seems absent because many weak processes are rare on human timescales, yet those rare processes matter because they control long-term change. The weak interaction also demonstrates that an interaction is not always about bending motion. Sometimes it is about opening a pathway between states that would otherwise be forbidden. When a nucleus decays, the key event is not a push in space. The key event is a change in the internal quantum state of the system, enabled by the allowed couplings of the theory. Gravity sits in a special position. For most laboratory quantum systems, it is so weak that it can be ignored. Yet at cosmic scales it dominates structure because it is always attractive, and it accumulates. Our best tested description of gravity is geometric, expressed as curvature of space-time rather than as a conventional force field in the same sense as electromagnetism. How to join that geometric description seamlessly with quantum field ideas at all scales remains an active frontier. Still, gravity fits the interaction theme. It is a universal coupling to mass energy that shapes how matter and light move, and it does so in a way that becomes unmistakable when you look at planets, stars, and galaxies. Even without a complete quantum theory of gravity, we can see how deeply the idea of interaction runs. Whether you describe it as curvature or as a field-like influence, gravity governs what changes are allowed for trajectories and clocks. Across these different cases, a steady principle holds. Interactions are constrained by symmetry and by conservation. Symmetries restrict what kinds of couplings can exist in a consistent theory, and conservation laws restrict which transitions can occur. Within those constraints, quantum theory assigns probabilities. This is why quantum randomness does not dissolve the world into chaos. Randomness lives inside guardrails. An interaction may allow several outcomes, but each outcome must respect the same accounting rules. Momentum must balance. Energy must balance. Other conserved quantities must balance as well. The world looks reliable not because it is deterministic in every detail, but because even its uncertainty is structured. Another idea that makes interactions feel less mysterious is emergence. At the microscopic level, an interaction is encoded as a coupling that transforms states and sets transition tendencies. At the macroscopic level, when enormous numbers of microscopic interactions average together, the result can look like a smooth classical force law. The rigidity of a solid is not primitive. It is a collective outcome of electromagnetic interactions among electrons and nuclei. The pressure of a gas is not a separate fundamental push. It is the average effect of countless microscopic collisions governed by the same underlying couplings. Even friction, which can seem like a basic force in everyday life, is better understood as an emergent outcome of electromagnetic interactions and energy transfer into many microscopic degrees of freedom. Force is often the name we give to the stable, averaged behavior of interactions when we stop tracking the details. This perspective also clarifies a common misunderstanding about virtual particles. In careful language, virtual refers to internal elements of a calculation, not to directly observable particles traveling through space. Virtual contributions encode how fields respond during an interaction, consistent with quantum principles and relativistic causality. You cannot place a detector halfway through the mathematics and catch a virtual particle. What you can do is measure final distributions, compare them with predictions, and find that the framework works with astonishing accuracy. In that sense, the exchange language is an accounting tool that helps organize calculations, not a literal movie of hidden objects. Modern theory adds another calming twist. You do not always need a complete microscopic story to make excellent predictions. In many regimes, you can use an effective description, a simplified model that captures the net influence of deeper processes without tracking every detail. If you probe low energies, many high-energy details influence your experiment only through a small set of measurable parameters, and the simplified theory remains accurate within its intended domain. This is not cheating. It is a disciplined way to respect scale, and it is one reason physics can be both deep and usable. Interactions can be described at the level appropriate to the questions you are asking. Interactions also explain why isolation matters. A perfectly isolated system is an idealization. In reality, everything is coupled to something. Stray fields, thermal agitation, background radiation, and material imperfections are all interactions in disguise. In delicate quantum devices, these unintended couplings can drain coherence into uncontrolled channels and blur the clean patterns you want to study. But that is not a failure of quantum mechanics. It is quantum mechanics doing exactly what it says it will do when a system is allowed to interact with a complicated environment. Information spreads, correlations disperse, and the sharpness of a quantum pattern becomes harder to maintain. Seen this way, force becomes an interface word, a human-scale handle on a deeper mechanism. Nature does forces by allowing fields to couple locally, by letting excitations scatter and transform, and by enforcing strict accounting across every exchange. The details can be intricate, but the principle is steady. Interactions are the grammar of change, and the measurable world is the set of sentences that grammar permits. There is a quiet existential reflection hidden in this picture. If everything that happens is shaped by interactions, then nothing is truly separate, including you. Your day was a sequence of couplings with the world, and you carried their traces in your body and mind. Now you can let those couplings soften and trust that the universe will keep balancing its accounts in the dark while you rest. Chapter 7. Emergence. How classical reality comes from quantum stuff. If quantum theory is the rulebook at the deepest level we currently use to predict the behavior of matter and light, then a natural question follows with quiet persistence. Why does everyday life not look quantum? Why do tables stay where they are? Why do planets follow smooth paths? Why do objects feel solid and definite? And why do we experience a world that seems to have stable properties even when we are not measuring them? The modern answer is not that quantum rules turn off at large scales. The answer is that classical reality emerges from quantum reality through a combination of averaging, amplification, and the relentless influence of the environment. Emergence does not mean illusion. It means that when many microscopic degrees of freedom interact, new effective descriptions become accurate and useful. A hurricane is not an illusion because it is made of molecules. A melody is not an illusion because it is made of vibrating air. In the same way, the classical world is not an illusion because it arises from quantum constituents. It is an effective layer of description that becomes overwhelmingly stable when the number of interacting parts becomes large, when interactions spread information quickly, and when certain patterns are amplified into records while others are washed away. One reason classical reality feels so stable is that macroscopic objects are not isolated. A cup on a table is constantly interacting with its surroundings. It exchanges photons with ambient light. It collides with air molecules. It vibrates internally, has thermal motion. It is in contact with the table, which is in contact with the floor, which is in contact with the building, which is in contact with the earth. These interactions are not incidental. They are what anchor the cup into a particular persistent set of macroscopic properties. In the quantum description, the cup plus its environment form a vast coupled system. The cup on its own is a subsystem, and subsystems quickly become entangled with what surrounds them. That entanglement spreads delicate quantum relationships outward into degrees of freedom you do not track. And in doing so, it makes some kinds of quantum behavior effectively inaccessible. This process is often discussed under the name decoherence, but the core idea can be stated without jargon. Certain quantum effects depend on maintaining precise phase relationships between alternatives. When a system interacts with an environment, information about those alternatives leaks outward. Once that information is widely dispersed, The alternatives no longer combine in the simple, controllable way they would in a carefully isolated laboratory system. The system's behavior becomes well described by an effective classical mixture of possibilities rather than a coherent quantum superposition that can interfere. The quantum rules have not been violated. They have simply played out in a larger space where the delicate relationships you would need to observe interference are no longer locally available. It is crucial to be accurate about what this does and does not explain. Decoherence explains why interference becomes extremely hard to observe for macroscopic objects and why certain preferred states become stable in practice. It explains why macroscopic records form and persist because the environment continually monitors and amplifies certain variables, such as position-like information, into many redundant copies. But decoherence by itself does not select a single unique outcome in a single run in the way people sometimes imagine. It explains why, for all practical purposes, different outcomes stop interfering and become effectively separate branches of behavior that do not recombine. The deeper question of why one particular outcome is experienced in a given run belongs to interpretation and to what quantum theory chooses to treat as primitive. For emergence, the important point is that classical-looking definiteness becomes the stable, effective description for large systems interacting with environments. Another pillar of emergence is coarse graining. No one measures every microscopic variable of a macroscopic object. You measure a temperature, not the speed of each molecule. You measure pressure, not the exact trajectory of each particle in a gas. You measure the shape of a table, not the quantum state of each electron in the wood. When you describe a macroscopic system in terms of a few collective variables, you are compressing vast microscopic complexity into a manageable description. Quantum theory allows this compression, and in many conditions it makes the compressed description not only convenient, but accurate. Many different microscopic states correspond to the same macroscopic temperature, for instance, and the macroscopic evolution becomes predictable because it is dominated by averaged behavior and because deviations tend to be washed out by the enormous number of degrees of freedom. This is where thermodynamics and statistical mechanics enter, not as separate subjects, but as the natural language of emergence. The classical laws of heat, work, and entropy describe how energy flows and how macroscopic order changes when you ignore microscopic details. In quantum physics, these ideas remain valid, but their foundation becomes clearer. A macroscopic state is typically a highly mixed state of enormous complexity, and what we call equilibrium is a state where, given the constraints, the system has distributed its accessible information so broadly across microscopic degrees of freedom that macroscopic observables stop drifting. Irreversibility, which seems to contradict the reversible nature of many microscopic laws, emerges because information about precise microscopic correlations becomes dispersed into degrees of freedom we do not track. The forward direction of time in everyday experience is tied to the growth of entropy and to the practical impossibility of reversing the full microscopic state of the universe around you. Emergence also explains why classical trajectories appear. In quantum theory, a free, isolated wave-like excitation can spread, but macroscopic objects are not free and not isolated. Their interactions with environments continually suppress the kinds of delocalized states that would lead to obvious spreading at human scales. In addition, When an object has a large mass and a well-defined momentum distribution at ordinary temperatures, the relative quantum uncertainty in its motion can be extremely small compared to the scales we perceive. Under those conditions, the probability distribution for position evolves in a way that is sharply peaked along a path that closely matches a classical trajectory. The path is not a fundamental line drawn by nature. It is an emergent feature of a distribution that remains narrow because of mass, environment, and constant monitoring through interaction. One of the most instructive places to see emergence is in the behavior of collective quantum phases of matter. Superconductors, superfluids, and certain magnetic materials involve quantum coherence on large scales, yet they still produce macroscopic behavior that can be described with relatively simple classical-like equations for currents, flows, and fields. This shows that emergence is not simply quantum becomes classical because quantum disappears. Instead, emergence is a selective process. Some quantum features become hidden, others become amplified, and in special materials, some quantum order can remain coherent over surprisingly large distances. The same underlying quantum rules can yield both classical-looking rigidity and exotic macroscopic quantum phenomena, depending on temperature, interactions, and isolation. The classical concept of an object having definite properties also emerges through measurement-like interactions with the environment. A macroscopic object is constantly scattering photons and colliding with molecules. Those interactions encode information about the object's position and orientation into the environment. Because the environment has an enormous number of degrees of freedom, that information becomes redundant. Many photons carry similar information about where the object is. Many air molecules carry similar information about the object's surface. This redundancy makes the object's classical properties stable in practice. They can be inferred by many observers in many ways without significantly disturbing the object. In a sense, the environment acts as a communication channel that broadcasts certain macroscopic facts. That broadcasting is part of why classical reality feels objective and shared. There is another element of emergence that is less often discussed, but just as important: amplification. A microscopic event becomes a macroscopic fact when it triggers a chain reaction that multiplies its effect. A single photon absorbed in a photodetector can trigger an avalanche of charge carriers. A small chemical change can trigger a larger reaction that becomes visible. A tiny mechanical displacement can be amplified by a lever or electronics into a readable signal. Amplification is physical. It requires energy. It produces heat. It creates durable changes in matter. Once an outcome has been amplified into a macroscopic record, it becomes extremely difficult to erase or reverse, because doing so would require undoing the changes in countless degrees of freedom. This is one reason measurement outcomes feel irreversible and classical. They are not simply observed. They are manufactured into the world through thermodynamically costly processes. At this point, it is tempting to say that classical reality is just what happens when quantum systems get big. That is too vague. The more accurate statement is that classical descriptions become accurate when three ingredients align. The first is large numbers of degrees of freedom, which make averages stable and fluctuations small relative to the scale of observation. The second is strong coupling to an environment, which disperses phase relationships and stabilizes certain macroscopic variables. The third is coarse-grained description, which focuses on collective observables and ignores microscopic details that are both inaccessible and irrelevant for the questions being asked. When these ingredients align, the classical world is not a separate realm. It is the natural effective behavior of quantum matter under ordinary conditions. This perspective also helps you understand why engineers can build reliable machines without solving the Schrödinger equation for every bolt. The reliability of classical mechanics and classical electromagnetism at macroscopic scales is itself an emergent blessing. It is the outcome of a world where quantum uncertainty is typically negligible at those scales, where decoherence is overwhelming, and where the relevant degrees of freedom are collective and robust. The quantum layer is still there, holding matter up, shaping chemical bonds, and enabling electronics. But the macroscopic behavior becomes stable enough that a simpler description is not only convenient, it is true within its domain. Emergence also has an honest boundary. If you isolate systems well enough and cool them enough, quantum behavior becomes visible at larger and larger scales. Interference experiments with larger molecules, coherence in superconducting circuits, and entanglement in engineered systems show that classical is not a universal limit written into nature. It is a regime. You can move out of that regime by changing the environment and the control. That is one reason quantum technology is possible at all. It does not create quantum effects from nothing. It simply prevents the environment from erasing them too quickly. So the classical world is not a denial of quantum strangeness. It is the world that quantum rules produce when they are embedded in a warm, noisy, interacting universe. The desk you sit at is made of quantum fields, yet it feels solid because the electromagnetic interaction and quantum statistics stabilize matter, and because the environment constantly reinforces classical properties through countless interactions. Your body is quantum matter, yet your experience is classical because information is amplified into stable patterns, and because your brain, like all macroscopic systems, operates in a regime where coherence is largely suppressed by environment and temperature. There is a quiet existential reflection here. Emergence suggests that the world you live in is a reliable surface formed from deeper rules, like a calm ocean surface formed from countless moving molecules beneath. You do not have to hold the universe in your mind for it to remain stable. Stability is what the universe naturally builds when many things interact. And if your day has felt messy or uncertain, it can be comforting to remember that order is not always something you must create. Sometimes it is something you are allowed to rest inside for a while, as the deeper layers continue their patient work. Chapter 8. Noise, Environments, and Why Isolation Matters. Quantum theory is often introduced as a set of deep principles, but it becomes truly understandable when you see how hard it is to protect those principles in the real world. The quantum rulebook is strict about what should happen for an ideal system prepared in a known way and measured with a well-defined apparatus. Yet the physical world is not made of ideal systems. Everything is embedded in an environment, and the environment is never perfectly quiet. This is why noise is not a side topic in quantum physics. Noise is the everyday condition under which quantum behavior must survive if you want to observe it cleanly. In ordinary language, noise sounds like a nuisance, like static on a radio. In physics, noise means uncontrolled degrees of freedom that couple to your system and disturb the patterns you are trying to predict. It includes thermal motion, stray electromagnetic fields, vibrations, cosmic rays, material defects, fluctuating charges, and the subtle electromagnetic activity of nearby electronics. Noise also includes information flow. Even if the system does not exchange much energy with the environment, it can still leak information about its internal relationships into the world around it. That leakage is enough to wash out interference and other delicate quantum effects. The world does not have to smash a quantum system to make it look classical. It only has to whisper to it persistently. This is why isolation matters. Isolation is not a metaphysical demand to keep something pure. It is a practical demand to keep the system's evolution dominated by the interaction you intend to study, rather than by countless unintended interactions. When a quantum system is well isolated, its state evolves in a controlled, predictable way, and your measurement statistics can be compared directly with theoretical predictions. When it is poorly isolated, the state becomes entangled with uncontrolled degrees of freedom. The predictive description becomes mixed, and your observed statistics start reflecting the environment as much as the system. In that situation, quantum theory still works, but you are no longer testing the clean rulebook. You are testing a complicated open system. The language of open systems is one of the most realistic parts of modern quantum physics. A closed system is a useful idealization, but almost everything that matters in laboratories and in nature is an open system. A molecule in a warm room is open because it collides with air molecules and exchanges photons. An electron in a solid is open because it interacts with lattice vibrations and impurities. A quantum device on a chip is open because it couples to the electromagnetic modes of its wiring, substrate, and surrounding circuitry. When you study such systems, you are not asking how an isolated quantum state evolves in perfect silence. You are asking how a quantum system behaves while it is being continuously influenced by the world. There are several ways the environment influences a quantum system, and each one leaves a different fingerprint. Sometimes the environment exchanges energy with the system, causing relaxation. An excited state can decay, and energy is emitted into the surrounding field or absorbed by a material bath. In other cases, the environment primarily scrambles phase relationships without strongly changing the system's energy. This is called dephasing, and it is one of the main reasons interference becomes hard to observe. There are also cases where the environment creates random shifts in parameters, such as fluctuating magnetic fields, leading to slow drift that accumulates over time. These processes are different, but they share a common theme. They push the system away from the clean, controlled evolution you would have in isolation. The key scientific point is that noise is not mysterious. It is interaction. It is the same physics as force, but uninvited and unaccounted for. When a system is coupled to an environment with many degrees of freedom, information and energy can flow into that environment in ways that are practically irreversible. The system's state becomes correlated with microscopic details of the environment, and because those details are not tracked, the system's behavior becomes effectively statistical in a richer way than the ideal quantum rulebook. This is not a failure of the rulebook. It is the rulebook applied to a larger coupled system, then reduced down to a subsystem description. One of the most important consequences of environment coupling is the loss of coherence. Coherence is the property that allows different alternatives to combine and interfere. In the state language, coherence corresponds to the presence of well-defined phase relationships that can influence future measurement statistics. When the environment couples to the system, it can acquire information about which alternative occurred, even if no human reads that information. Once that information is out in the environment, interference becomes suppressed because the alternatives are no longer part of a single coherent description accessible to your measurements. The system has not been destroyed. It has become entangled with the environment in a way that makes certain quantum signatures inaccessible. It is important to avoid repeating the same idea too broadly here. In the previous chapter, the role of environment in classical emergence was framed at the level of macroscopic objects and stable records. Here the focus is narrower and more experimental. The question is, why do quantum experiments require such careful engineering? The answer is that quantum behavior is not fragile because nature is inconsistent. It is fragile because the information that defines a quantum state can be dispersed into the environment through many tiny interactions, and once dispersed, it is effectively unrecoverable. The experimenter's job is to slow that dispersal, to understand the channels through which it occurs, and to design protocols that either avoid those channels or compensate for them. Temperature is one of the simplest ways to see why noise is so pervasive. At non-zero temperature, every material contains thermal motion. Charges fluctuate, atoms vibrate, and electromagnetic fields in the environment carry random excitations. These fluctuations create random perturbations that couple to quantum systems. Cooling reduces those excitations and can make quantum behavior much easier to observe. This is why many of the most striking quantum experiments are done at low temperatures or in ultra-high vacuum. The goal is not to make the system more quantum. The goal is to remove the chaotic background that constantly nudges the system and steals coherence. But temperature is not the only source. Electromagnetic noise can come from the very electronics used to control the experiment. A wire is not just a wire. It supports electromagnetic modes that can carry away energy and information. A nearby surface can host fluctuating charges. A substrate can host defects that behave like tiny two-level systems, absorbing and releasing energy unpredictably. Mechanical vibrations can modulate distances and fields. Even background radiation, including cosmic rays, can deposit energy and create rare but disruptive events. When experimentalists talk about isolation, they are often talking about reducing all these couplings to a level where the desired interaction dominates and the noise can be modeled as a small correction. This brings us to an important point about the scientific method in quantum physics. Because noise is unavoidable, the goal is rarely perfect isolation. The goal is known isolation. A well-designed experiment does not merely try to eliminate every interaction. It tries to characterize the remaining interactions so that the theory can include them. In other words, the environment is not always the enemy. Sometimes it is part of the model. When you understand the coupling, you can predict how fast coherence decays, how populations relax, and how measurement outcomes will drift. You can then compare those predictions to data, and the match becomes a test not only of quantum theory, but of your understanding of the system's environment. This is one reason open system quantum physics is both challenging and beautiful. It sits at the boundary between ideal principles and the messy richness of the real world. It shows that quantum theory does not require a pristine universe to function. It requires only that you specify what you are including in the system and what you are treating as external. When you do that honestly, the framework remains consistent. Isolation matters not only for observation, but also for control. Quantum control means steering a system into a desired state, maintaining it, and manipulating it in a predictable way. In quantum technologies such as precision sensors and quantum computing devices, control must be maintained long enough to perform meaningful operations. Noise sets a practical clock. It determines how long the system retains the information that defines its quantum state. If the environment scrambles that information too quickly, the device cannot function as intended. This is not a philosophical problem. It is an engineering problem grounded in the same physics as everything else. Even outside technology, isolation matters for the clarity of fundamental tests. Many iconic quantum experiments can be reinterpreted as battles against the environment. Interference requires a system that can follow multiple alternatives without leaking which alternative information into the surroundings. Bell-type tests require careful separation and timing to prevent ordinary influences from mimicking quantum correlations. Precision spectroscopy requires shielding from stray fields and control of temperature to prevent line broadening and drift. The cleanest experiments are not the ones with the most dramatic stories. They are the ones where noise has been reduced and characterized so thoroughly that the remaining patterns directly reflect the underlying quantum rules. There is also a conceptual lesson in the word environment. The environment is not a single thing. It is whatever you have decided not to include in the system description. That means environment changes with context. In one experiment, the environment might be the electromagnetic field modes outside a cavity. In another, it might be the lattice vibrations in a crystal. In another, it might be a background gas in a vacuum chamber. The environment is defined by the boundary of your attention and control, not by a universal category. This is why the same physical object can look highly quantum in one context and classical in another. Change the boundary and you change the relevant state description. If you let all of this settle, it becomes clear why the quantum world is not always obvious. Quantum theory is not describing an exotic realm that exists only in special places. It is describing the fundamental behavior of matter and fields everywhere. But the signatures we associate with quantumness, such as long-lived coherence and visible interference, require that the system be protected from constant interaction with its surroundings. The ordinary world is not less quantum. It is more connected. It is full of interactions that spread information so quickly that the classical layer becomes the most stable, practical description. And there is an existential reflection that fits naturally here. Noise is what happens when everything touches everything else, when the universe refuses to leave any system perfectly alone. That can sound unsettling, but it can also be comforting. Your own mind has been interacting with the world all day, absorbing signals, stresses, and small disturbances. Now, as you rest, you can allow those interactions to fade into the background, like noise settling when a room goes quiet. The universe will keep coupling and evolving, but you do not have to keep track of it. You can let go, knowing that even in a noisy world, the deeper rules remain consistent. and you are allowed to sleep inside that consistency. Chapter 9. What quantum theory refuses to explain. On purpose. Quantum theory is famous for being strange, but its deepest strangeness is not the one people usually point to. The most unsettling feature is not that microscopic systems can behave in ways that defy everyday intuition. The most unsettling feature is that the theory works extraordinarily well while remaining deliberately silent about certain kinds of explanation we instinctively want. It is not that physicists have forgotten to add the missing pieces. It is that the framework, as it is commonly used, is built to be a predictive rulebook, and it draws a boundary around what it promises to deliver. Inside that boundary, it is precise. Outside that boundary, it often says, in effect, this is not the kind of question the theory answers. To understand this boundary, it helps to separate two meanings of the word explain. One meaning is predictive explanation. A theory explains when it correctly links conditions to outcomes and does so with internal consistency. In this sense, quantum theory explains a vast range of phenomena: atomic structure, chemical bonding, the behavior of solids, the properties of light, and the outcomes of carefully designed experiments. Another meaning is narrative explanation. We want a story about what is really happening in a single run, even when no measurement is performed. And we want that story to resemble the classical picture of objects carrying definite properties through time. Quantum theory does not consistently provide that story. It can be supplemented with interpretational stories, but the core formalism remains agnostic, and in practice, it refuses to turn that agnosticism into a single mandated narrative. This refusal is not an accident of history. It is tied to the way the theory is structured. The framework begins with preparation procedures, assigns a state description, specifies how that state evolves under chosen conditions, and then provides probabilities for measurement outcomes when a measurement is performed. What it gives you are statistics, not a deterministic script for each event. When you ask, why did this particular outcome happen in this particular run? The formalism typically answers only by giving you the probability of that outcome given the state and the measurement. It does not offer a further causal mechanism for the individual draw. In that sense, quantum theory treats the individual outcome as a primitive event that is not further decomposed within the theory. Many people find this unsatisfying, and that discomfort has fueled a century of debate. But it is important to be clear about what is being debated. The debate is not about whether quantum theory predicts correctly. In its tested domains, it does. The debate is about what the formalism is saying about reality between preparations and measurements, and whether the state is a description of the world itself or a description of our information about the world. Quantum theory, as a predictive framework, does not force a single answer. That is one of the things it refuses to explain. What exactly the state is, in ontological terms, a related refusal concerns counterfactual certainty. In classical thinking, it feels natural to say that a system has definite values for many properties, even if you choose to measure only one of them. You can imagine measuring position, but you believe the object also has a momentum, and if you had measured momentum instead, you would have simply revealed it. Quantum theory does not generally support that picture. It provides probabilities for the outcomes of whichever measurement you choose, but it does not assign definite simultaneous values to all possible measurement choices in a way that remains consistent with experimental results. This is not a philosophical preference. It is constrained by the structure of the theory and by the way different measurements relate to one another. The framework refuses to tell you what the unmeasured values really were, because that kind of joint assignment does not always exist in a consistent way. This leads into a subtle but essential point about what quantum theory claims. Quantum theory claims that measurement outcomes are distributed according to specific rules determined by the state and the measurement. It does not claim that every measurement simply uncovers a pre-existing property that was sitting there all along. In some special cases, you can prepare states where certain outcomes are effectively guaranteed for a given measurement. And in those cases, it is tempting to talk as if the property was definite. But the general case is different. The theory is built to predict measurement statistics, not to provide a hidden inventory of all properties the system carries, regardless of how you interact with it. Another refusal appears in the question of where the boundary is between the quantum system and the classical measuring device. In practical work, physicists model a system quantum mechanically and treat the measuring apparatus classically or semi-classically, because the apparatus is large, noisy, and designed to produce stable records. This works extremely well. But if you insist on a fully universal description, you can ask, why is the apparatus classical at all if it is made of quantum constituents? The modern technical answer involves open systems and decoherence, which explain why classical-like behavior is stable for macroscopic objects. Yet even with those tools, the theory often refrains from declaring a single sharp boundary. The framework works without needing one. It allows you to shift the boundary, treating more of the apparatus as part of the quantum system if you like, and as long as you include the relevant interactions, the predicted statistics remain consistent. The theory refuses to provide a unique, fundamental cut because the predictions do not require it. There is also a refusal concerning meaning. Quantum theory can tell you the probability of finding a particular outcome, and it can tell you how those probabilities change with time and with experimental settings. It does not tell you what probability is in the metaphysical sense. Is it a measure of objective chance in the world or a measure of rational belief given information? Different philosophical positions exist, and quantum theory can be used within each of them. The formalism itself does not settle the argument. In practice, physicists use probability as a tool, as the correct way to connect state descriptions to experimental frequencies. The theory refuses to explain the ultimate nature of probability because its primary job is to constrain what can be predicted and verified. Some of these refusals can be sharpened by results in the foundations of quantum mechanics. There are theorems showing that certain classes of hidden variable explanations, where outcomes are determined by underlying variables not included in the standard description, cannot reproduce the full set of quantum predictions if they also satisfy certain intuitive conditions, such as locality in the relativistic sense or non-contextual assignment of properties. The details are technical, but the implication is calm and important. The desire for a classical-style underlying story is not unconstrained. Any deeper story must pay a price, giving up or modifying some assumption that feels natural in classical thinking. Quantum theory refuses to provide a deeper story for free because the data do not allow a simple classical upgrade. At the same time, it is crucial not to misstate what these foundational results prove. They do not prove that reality is mystical or that consciousness creates outcomes. They do not prove that nothing is real until observed in a dramatic everyday sense. They show that if you want an underlying model that reproduces quantum predictions, you must be careful about which classical intuitions you keep. Quantum theory itself remains a pragmatic framework that predicts outcomes for experiments. When people attach larger philosophical conclusions to it, those are interpretations, not additional experimentally confirmed content. The core theory refuses to endorse a single metaphysical add-on because multiple add-ons can coexist with the same predictive success. Another boundary is the refusal to supply a final explanation for why the laws are quantum at all. The theory provides a successful structure, but it does not tell you why nature chose this structure rather than some other. In physics, this is common. Newton's laws did not explain why mass exists. Maxwell's equations did not explain why there is a particular speed of light. Even general relativity does not explain why spacetime has the dimensions and constants it has. Quantum theory, similarly, is a framework that organizes observations and predictions, not a final answer to why the universe has that framework. When people ask, "Why is the world quantum?" the honest answer is that this is a deeper question about the origin and uniqueness of the laws, and it sits outside what the theory itself is designed to answer. Quantum theory also refuses, in its standard form, to resolve every tension between itself and gravity. Quantum field theories describe the other interactions extraordinarily well, and general relativity describes gravity as geometry. We can successfully use both within their domains, and we can combine them approximately in many practical situations. But a complete theory that unifies them at all scales is still an open problem. In that sense, quantum theory refuses to explain what happens in regimes where both quantum effects and strong gravitational effects are essential simultaneously. We can make informed models and explore candidates, but we do not yet have a universally accepted framework with the same level of tested precision as we do for the other interactions. This is not a failure unique to quantum theory. It is the edge of current physics. There is also a quieter refusal that matters for how people relate to the theory. Quantum mechanics does not promise comfort. It does not promise that the world will be describable in the most human-friendly way. It promises something else, an internally consistent method for predicting the statistics of measurement outcomes given controlled preparations and known interactions. This promise is modest, but it is also astonishing in its reach. The theory has survived countless tests precisely because it does not overpromise. It does not claim to give you a detailed movie of microscopic reality that you can watch with your imagination. It claims to give you a reliable rulebook for what you will observe, and it does. That modesty is one reason quantum theory feels incomplete to many minds. We are built to desire narratives. We want a picture of what happened when no one was looking, and we want that picture to be uniquely determined. Quantum theory often declines to provide it. But there is another way to read this. The theory's refusal is a kind of scientific discipline. It draws a line between what can be asserted on the basis of reproducible experimental evidence and what becomes a matter of interpretational preference. In doing so, it protects physics from becoming an arena for unconstrained storytelling. So what does quantum theory refuse to explain on purpose? It refuses to explain individual outcomes beyond their probabilities. It refuses to assign definite values to all possible measurements simultaneously in a universal way. It refuses to select a single metaphysical interpretation as part of its tested content. It refuses to define a unique classical quantum boundary as fundamental. It refuses to provide a final why for its own structure. And at the frontiers, it refuses to be the last word where gravity must be fully quantum. These are not flaws in the theory's predictive core. They are boundaries that keep the theory honest about what it can claim. There is an existential reflection that can sit gently alongside this honesty. Not knowing everything is not the same as being lost. A rulebook can be dependable even when it does not provide a story you can picture. And there's a quiet relief in realizing that reality does not require your understanding to be real. The universe can be lawful and stable without offering you a final narrative. And tonight you can let that be enough, allowing the unanswered questions to remain unanswered while you rest. Chapter 10. Why it still works so well, the quiet power of the framework. Quantum theory has a reputation for being unsettling, but its most important trait is not its strangeness. Its most important trait is reliability. It is the framework that keeps producing correct predictions across an enormous range of experiments, from the structure of atoms to the behavior of solids, from the properties of light to the engineered control of quantum devices. When a scientific theory works this well, year after year, across different laboratories, different materials, and different measurement technologies, the deeper question changes. Instead of asking why quantum theory is weird, we can ask why it is so steady. What is it about the framework that makes it quietly powerful? Part of the answer is that quantum theory is built from a small set of structural commitments rather than a large catalog of ad hoc rules. It begins with a disciplined separation between preparation, evolution, and measurement. You specify how a system is prepared, you specify the conditions under which it evolves, and you specify the measurement procedure. The framework then provides a single consistent way to connect these elements to predicted statistics. This structure is not merely convenient, it is a form of scientific honesty. It forces every claim to be tied to something you can actually do in the lab and something you can actually record. Because the framework is structured, it is also portable. Once you learn how to describe a state and how to compute measurement statistics, you can apply the same logic to electrons in an atom, photons in an optical cavity, vibrations in a crystal, or collective modes in a superconductor. The details differ, but the grammar remains the same. This is a hallmark of a deep theory. It uses a stable language that can be reused across domains without being rewritten from scratch each time. Another reason it works so well is that it respects symmetry at a fundamental level. Symmetry is not only aesthetic, it is a constraint that filters what is allowed. When you demand that the laws look the same under shifts in time and space, under rotations, and under deeper internal transformations, you restrict the possible structures of the theory. Quantum mechanics and quantum field theory are built to encode these invariances in a precise way. The result is that the framework is not free to drift into contradictions. It is held together by the requirement that its predictions remain consistent when you change your viewpoint or when you compose systems into larger systems. This symmetry discipline is also why conservation laws remain so dependable within quantum physics. Energy, momentum, angular momentum, and charge are not merely habits the universe happens to keep. They are bookkeeping necessities that follow from invariances of the laws. When those invariances are built into the framework, conservation becomes part of the foundation, rather than a set of separate rules that must be remembered and applied by hand. In practice, this means quantum theory is constrained in ways that protect it from producing impossible results. Even when individual outcomes are probabilistic, they are probabilistic in strict accounting guardrails. That combination of flexibility and constraint is one reason the theory can be both subtle and stable. The framework is also powerful because it is inherently statistical in the right way. It does not pretend to predict individual outcomes when the world does not support such predictions. Instead, it predicts distributions. This is not a retreat. It is in alignment with what experiments actually provide. Every real experiment involves finite sampling, noise, and uncertainty in apparatus settings. A theory that insists on deterministic detail at the wrong level can become fragile because any small untracked influence can break it. A theory that predicts stable statistical patterns can remain robust even when the laboratory is imperfect, as long as the imperfections are understood and controlled to within known limits. Quantum theory thrives in this environment because it was built to speak the language of experimental frequency from the start. A related strength of quantum theory is modular. You can treat part of the world as the system and treat the rest as the environment, and then refine the boundary when you need more accuracy. This is not a loophole that makes the theory unfalsifiable. It is a pragmatic way of matching the model to the question. If you are studying an isolated atom in a trap, you can model it as a nearly closed system and predict coherent behavior. If you are studying an atom in a warm gas, you can include open system effects and predict relaxation and broadening. The same framework supports both descriptions without contradiction because it is built to handle composition and reduction. It acknowledges that systems interact, and it gives you tools to describe what happens when you track only part of a larger coupled reality. This modularity is also what allows the theory to connect the microscopic and macroscopic worlds without changing its core grammar. On one hand, quantum mechanics explains the stability of atoms and the structure of chemical bonds, which in turn explain why matter has the properties it does. On the other hand, the same framework explains how classical behavior emerges when systems are large, warm, and strongly coupled to their environments. It does not need a separate set of classical laws pasted on top. Classical physics becomes an effective limit, a reliable approximation that emerges when certain conditions are met. The power here is not that quantum theory makes the world complicated. It is that it makes a complicated world compressible into layers of description that each work where they should. Another deep source of strength is renormalization and scale thinking, even if you never write the formal machinery down. Many of the most accurate quantum field theories are built with the understanding that what matters depends on the scale at which you probe. At low energies, many high-energy details affect your experiments only through a small number of effective parameters. This is why quantum theory can be both extremely accurate and not overwhelmed by infinite microscopic complexity. It lets you build effective theories that capture the relevant interactions at a given scale without claiming to know every detail of physics at all scales simultaneously. This is not an excuse for ignorance. It is a disciplined hierarchy that has been repeatedly validated in practice. Precision is another pillar. Quantum electrodynamics, the quantum field theory of electromagnetic interactions, has been tested against experiments with extraordinary accuracy. The agreement between prediction and measurement is not merely qualitative. It reaches levels of precision that are among the strongest in the history of science. This matters because it shows that the framework is not surviving on vague interpretational flexibility. It is surviving because its quantitative predictions are correct to an extent that leaves little room for alternative structures that behave very differently. A theory can be philosophically uncomfortable and still be physically exact, and quantum theory is the clearest example of that. The framework also works well because it is careful about what it claims. It does not insist on a single metaphysical interpretation, and that can feel unsatisfying, but it also protects the theory from being broken by arguments about meaning rather than evidence. The core formalism makes operational commitments, and those commitments are testable. Interpretations can differ on what is happening between measurements, but they must all reproduce the same observable statistics in the domains where quantum theory has been confirmed. The refusal to legislate metaphysics as part of the predictive core keeps the theory focused on what it can defend experimentally. This focus has practical consequences. It allows quantum theory to guide technology without requiring philosophical closure. Transistors work because quantum theory describes electron behavior in solids. Lasers work because quantum theory describes light-matter interaction and stimulated emission. Magnetic resonance techniques work because quantum theory describes the behavior of spins in fields. Precision clocks work because quantum transitions provide stable frequency references. These successes are not merely applications. They are confirmations that the framework captures deep regularities of nature. The world is allowing us to build devices that depend on quantum rules, which is a form of evidence that is hard to dismiss. Another reason the framework remains powerful is that it has clear failure modes. When quantum predictions do not match experimental data, it is rarely ambiguous what you should check. You examine the preparation, the isolation, the measurement calibration, and the model of the environment. You test whether an assumed symmetry is actually broken in your setup, whether an overlooked interaction is present, whether thermal noise is dominating, or whether your effective theory has been pushed beyond its intended scale. This gives the framework a kind of self-correcting clarity. It does not guarantee that every experiment is easy, but it provides a structured approach to diagnosing mismatch rather than leaving you with endless interpretational wiggle room. Of course, the fact that quantum theory works extraordinarily well does not mean it is the final word on physics. There are frontiers where we expect modifications or deeper unification. Gravity remains the most prominent example. We can use quantum theory and general relativity together in many practical regimes, but we do not yet have a universally accepted theory that unifies them at all scales with the same level of tested precision. There are also questions about the origin of the laws, the values of constants, and the nature of space-time at the smallest scales. But these are not cracks in the everyday functioning of quantum theory. They are horizons. They mark where the framework may be embedded in something deeper, not where it stops being reliable in the regimes where it has already been validated. So the quiet power of the framework is not that it gives you a comforting picture. It is that it gives you a stable language for prediction, constrained by symmetry, conservation, and consistent probabilistic rules, adaptable across scales, and confirmed by precision. It is powerful in the way a well-designed map is powerful. It does not recreate the landscape in your mind, but it reliably tells you what you will find when you walk. And there is an existential softness in that reliability. You can spend your life chasing certainty and still find that the deepest theories do not promise it in the way you imagined. Yet the universe remains steady anyway, held together by rules that do not require your attention to keep working. If your day has been heavy, you can let it go here, trusting that reality will continue its quiet accounting in the dark, and you can rest inside the fact that the world is lawful even when it is strange. And that's the quiet power of quantum theory. Not a magical story, but a rule book that keeps predicting reality with astonishing calm. If your thoughts feel a little softer now, let them drift. Nothing you need to solve tonight. And if you're still awake, I've got another sleep science video waiting for you on the channel. Just pick the next one and let it carry you the rest of the way. Sleep well, my friend, and sweet dreams among the stars.